So, good afternoon, everyone. I'm Silbe Kim from Korea University, and it's a great pleasure to talk about our work called VUDDY, a scalable approach for vulnerable code clone detection. So before getting started, I want to ask you a question. How many number of unpatched known vulnerabilities do you think you have in the firmware of your smartphone? I mean, not the unknown vulnerabilities, but the known vulnerabilities. In my smartphone, through the use of our approach, I could find more than 200 unpatched CVE vulnerabilities in the firmware of my smartphone. So it's a lot more than we can normally expect. Here's the motivation. The number of open source software is increasing worldwide, and many people claim that the growth rate is exponential. And in this situation, the number of code clones, which are the reused code fragments, are also proliferating. So one point we're focusing on here is that code clones are being one of the major causes of vulnerability propagation. So for example, last year we had a dirty cow vulnerability discovered from the Linux kernel, and look what happened to all the other operating systems that use kernels as their basis. They were affected by the same vulnerability. And also, the same vulnerability propagated to the devices that use these OS operating systems. So that means we have a lot of vulnerable code clones in this real world. So the problem here we want to tackle here is the scalable and accurate detection of vulnerable code clones. The scalability, of course, it is important because software systems are getting bigger and bigger. For example, now Linux kernel has more than 25.4 million lines of code, and a firmware of smart TV consists of more than 35 million lines of code, in which it contains Linux kernel and Chromium OS and a lot of software libraries. So we need a scalable system to efficiently detect vulnerabilities from these large softwares. And also the accuracy is obviously it is important because for these kinds of static analysis approaches, false positive leads to increased efforts and time for researchers or anyone who is inspecting the software to manually go through every false alarms. So previously, many approaches that tried to tackle this similar problem was there were previous approaches, but there was a visual tendency of the trade-off between accuracy and scalability. And one notable exception here is the redebug, of which used the line level matching technique, but it still had a lot of false positives. So the goal of us is to get there to the area of the question mark, where we can achieve both the high accuracy and high scalability simultaneously. So we're proposing a method called VUDDY. And before explaining every rationale behind VUDDY, I want you to watch a short video, which is the result of our implementation. So basically, it's a web-based platform where you can upload a pre-processed index file and then get the results like that. So when you upload the index file, you can see that there are 234 vulnerable code clones detected with the yearly distribution of CVEs, where you can see that a number of recent vulnerabilities are not patched in CVSS and CW distribution. And also, you can browse through the source tree of your project, where you can see a number of vulnerabilities are spread through a lot of source code files. And clicking on the leaf node, you can also see what is the patch to fix the vulnerability in your code. So VUDDY, we aim to search for vulnerable code clones, and it scales beyond 1 billion lines of code target. And it detects both known and unknown vulnerability with a low false positive rate. And here's the overview of VUDDY. So we can have a bunch of vulnerable functions and a target program, and we can fingerprint them to generate fingerprint dictionaries of vulnerable functions and fingerprint dictionary of target functions. And then the vulnerable code clone detection is going to be a dictionary comparison. So what you want to do first is to collect vulnerable code. We leverage a standard vulnerability patching process to get vulnerable code fragments. So when you have a vulnerable code, you can write a CVE patch or any vulnerability patch and apply it to get the new fixed code. So if we apply this procedure reversely, like this, from software repositories such as Android Git repository or Linux kernel repository or anything, and you can extract every CVE patch from them to reconstruct the old vulnerable code. And the collection of these old vulnerable codes are going to be inserted into our vulnerability database. Now let's see how we fingerprint the program. First of all, we retrieve all functions from a program. And let's say this program consists of 3 different functions. And then we apply abstraction and normalization to the retrieved functions. And details about abstraction and normalization is going to be given in a minute. And then to the strings that to which the abstraction and normalizations are applied, we can calculate the length and hash values of these strings. And then we can store everything in a dictionary by using the length values as keys and the corresponding hash values that share the same key as a list that is mapped to the key values. So that's one exemplary fingerprint dictionary. And here's the explanation about the abstraction and normalization. We are applying abstraction and normalization because we want VUDDY to be resilient to common code modifications after code cloning, such as variable renaming or data type, changes of data type, things like that. It keeps moving. So we transform each and every function in a software by replacing formal parameters, local variables, data types, and function names to distinct common identifiers. And then remove every comment, tabs, white spaces, carriage returns, line feeds, and conduct a lowercase conversion so that the results of abstraction and normalization to be the string that is shown below. So now, vulnerable code clone detection is as simple as comparing 2 fingerprint dictionaries, and one of the dictionaries is going to be a fingerprint dictionary of vulnerable functions, and the other is going to be a fingerprint dictionary of target functions. And let's say we have these values in each of the dictionaries. So we first conduct a key lookup, and the lookup of key value 20 is going to be a hit, and then we proceed to a hash lookup. And here we found one hash value in common, which is the code clone that we're looking for. And if there's no match in key lookup, then we don't have to proceed to the hash lookup. Also in this case, because the other dictionary doesn't have the key of 22, we don't have to proceed to the hash lookup. So at last, we can conclude that our target program contains one vulnerable code clone, which has a hash value of C9, C9 4D9910. And if we take advantage of something like inverted index file, then we can retrieve the vulnerable function that we're looking for, like that. Now let's proceed to performance evaluation and case study. To evaluate the scalability of VUDDY, we collected more than 25K GitHub projects which had at least 1 push records and which has gotten more than 1 stars during the period of January 1st and July 28th of 2016. And we measured the execution time when varying size of randomly selected target programs are given to our approach VUDDY and CCFinderX, Deckard, VDebug, and Sorcerer CC, which are 4 of the state-of-the-art tools for clone detection. So, as you can see in the graph, Deckard did not scale beyond 10 million lines of code target, and please notice that the Linux kernel now contains more than 25 million lines of code, which means Deckard is not enough to apply to the real-world programs scalability. And CCFinderX managed to handle 100 million lines of code, but not beyond. And for Sorcerer CC, it has shown explosive increase of required time when it tried to get to the 1 billion lines of code target. However, VUDDY and VUDDY both managed to survive in this scalability evaluation. And in fact, VUDDY could scale to the whole 25K GitHub projects, which contains 8.7 billion lines of code. So we can say that VUDDY is very, very scalable. And for accuracy evaluation, we selected Apache HTTP server as our target, which contains 350K lines of code. And in terms of true positive, the tool named CCFinderX could find 2 more true positive cases than VUDDY did, because they are leveraging a token level granularity, which is a finer granularity than the function level granularity, which VUDDY uses. However, in terms of false positive, CCFinderX have generated 63 false positive cases, whereas VUDDY had no false positive at all. And we also conducted an in-depth comparison between VUDDY and VUDDY by detecting vulnerable code clones in an Android smartphone's firmware, which contains 15 million lines of code. And the pre-processing time for VUDDY and VUDDY were 17 minutes and 11 minutes, respectively. However, the clone detection time of VUDDY only required 1.09 seconds, whereas VUDDY required 17 minutes. Moreover, VUDDY generated no false positives, even though the target repository is very, very large. It was an Android firmware. However, VUDDY had 1,888 false positive cases. So 5 of the security researchers in our lab had to spend a week to manually verify these are false positives. Now, you should know that the generated fingerprints, once they are pre-processed and a fingerprint is generated, then they can be reused for good. So the actual clone detection time, if we are testing a same software over and over again, then VUDDY can do it in about a second. So what I want to claim here is that the actual detection time of VUDDY in practice is faster than VUDDY by the factor of about 1,000. Now here are some cases where VUDDY effectively found some of the unknown vulnerabilities in real softwares. One of which is the unknown vulnerability detected in Linux kernel, even in the latest stable version of last week. And the original vulnerability was in ext2, 3, and 4 file systems, and the patch for that was released in year of 2008. Of course, in the ext file systems, the patch is applied. However, in a file system called NILFS2, if you look at the source code of these 2 file systems implementations, we can easily suppose that the implementation of NILFS2 was taken from ext file systems. They cloned their code and modified a bit. And so because of that reason, the same vulnerability, the similar vulnerability exists in the NILFS file system, but not patched until now. So we could trigger a printk flood and denial of service in CentOS version 7 or Ubuntu 14.04. And here's another example. We could have found a 0-day vulnerability in Apache HTTP server to 2.4.20 through 2.4.25 because these versions of HTTP server daemon uses unpatched old XPath library for parsing XML files. And this library is vulnerable to CVE 2012-0876, so we could easily trigger a #DOS attack to the server daemons by sending a crafted XML packet. So as you see in the screen capture, we made the server daemon to consume 100% CPU. So in summary, VUDDY is an approach which is capable of detecting software vulnerability using a database of previously security patched functions. And applying abstraction to the functions enable identifying unknown vulnerable functions while still maintaining a low margin of errors. VUDDY had really low false positive rate. And also, the function level granularity and length-based filtering reduces the number of signature comparisons, guaranteeing high scalability. VUDDY could process 8.7 billion lines of code easily. And last but not least, It's provided as an open web service, so you can test our implementation at iotcube.net. So if you're interested in our research, you can come to the website and use this tool to test your programs and get some interesting results. So with that, I'll conclude my talk and open to any questions or comments. Thank you.
Any questions?
Hello, thank you for the talk. I'm Tomasz from Qualcomm. I have two questions. So the first one, as if I understand correctly, there is some flexibility when it comes to clone detection. For example, the names of variables and functions can differ. Will it still work when the structure of the function was slightly different? How much flexibility is there?
So the coverage of VUDDY is type 2 clones, which is sometimes called renamed clones. So if some of the statements are inserted or deleted, then VUDDY cannot detect such cases.
Thank you. And the second question is, what would you say is the main reason for low false positive rate?
That's because we're using the function level granularity. Function conveys both the syntactic and semantic informations, and it's designed to be serve a certain purpose, as you know. So I think that's why we have low false positive rate.
Thank you very much.
Thank you very much.
Hello, this is Siu from Purdue University. Do you mind if you go back to the slide where you show the ext2 and the other FS? I'm actually curious. This might be. Can you go back? Yeah, so this one.
This one?
I'm actually curious. This might not be that relevant to your technique, but do you know why in the ext2 source code on the left-hand side they have the NILFS DR entry on the fourth line? Like, is it like used also? Like, how is the ext2 using NILFS2 as well?
Okay, if we follow through the ext2_get page function or NILFS_get page function, then the two functions look very similar except for the names of the functions they call. So by that, I could suppose that, okay, the writers of the NILFS2 file system might have cloned some code, some portion of the ext file system's implementation.
Right, so I'm curious that actually in the ext2 code, they have the fourth line is NILFS dir entry. So it looks like actually the ext2 file, like the code is copied from NILFS.
Sorry, could you repeat the question?
So look at the line 4, you have some NILFS dir entry. So what is it doing in ext? So, like, to me, I'm just curious. It looks like they're also copying from the other side.
So the code on the left-hand side, I think that's a typo.
Oh, okay.
So that's supposed to be the ext2. I'm sorry.
Okay, no worries. Yep, thank you.
Thank you very much.
All right, so just one last, perhaps less important question.
Yep.
It seemed like you were showing us this bug and the bug in Apache, which are unpatched still, or have they been patched?
Sorry?
The bug here, which sort of feels like you said it exists in existing the Linux kernel, the newest one from 1 week ago, and the bug in the next slide, which is on an Apache case here. So have these been patched yet?
These are not patched yet, and the Apache security officer, someone, they said that the new version of HTTPD is not affected anymore because they have updated the expect library.
Okay. All right, thank you. Thank you so much.
Thank you very much.